This is the 44th lecture in a course on single agent search. And in this lecture, we're going to pick up from some of the ideas that were brought up in the last video. And the last video went into them at a very high level of detail, or at a very coarse level of granularity. And in this video, we're going to look at them in quite a bit more detail. And so the idea that's primarily that we're going to look at today is an idea called transit routing, but it's an idea that's related to a broader set of techniques that have been developed. Most of these developments have come out of the road networks community, and they're about observations that were made once a large number of road networks were available. They began to study and find the properties of these road networks, and they discovered that they have certain properties that allow us to do things like all-pair shortest path computation in efficient ways. And so at the high level, we're going to do transit routing, as I said. Which is a technique that was introduced around 2006, 2007, some early papers on that. But what we'll see is that it's related actually to a higher level of theory. So transit routing is a high level idea that we can do searches through transit points, and that we can do this very efficiently. But before I go into a description of transit routing, I want to just talk a little bit about the theory behind this. And the theory here is an idea called highway dimension. And there's a nice paper that goes and describes some of the background behind this by Abraham et al. In 2010. And the idea of highway dimension, of course, it sounds like highways, so it is something thinking about highways. And I'm going to draw a picture here that'll help illustrate what's going on. So you could imagine that you are in a city, and let's not think about a city like Los Angeles, maybe that's a very dense city with sort of city upon city upon city, but maybe we're thinking a little bit more broadly, at least for what we're analyzing here. So we could think of a city like Denver. And if we look at Denver, I'm not going to be precise geographically here, but we sort of see there's Denver and there's a bunch of open space around Denver. And so if you want to go from Denver to anywhere else sufficiently far, so this is just some sort of far distance, then if I think about some shorter distance inside here and say, how many possible ways are there to get from the city of Denver to other locations that are far away? And what you'd find is that there are not actually very many options that you have, because freeways are expensive. Then what you'd see is something like this is basically, well, you could head off to the west, you could choose to head off to the east, you could head off down to the south, and you could head off to the north. But there's actually not going to be that many more options besides that. And so if I think about if I'm going sufficiently far, and then we ask this question of how many, when I'm going to a large distance, how many points are there at some smaller radius? And the exact constants here don't matter too much, but we might say, for instance, that this is some radius 4r, and this is some radius r here. Okay. And the question is, how many points are there? Going from, if I'm going to go to some sufficiently long distance, whatever r happens to be, what do I expect to find? And if the answer is that there's a lot of points here, so you could imagine a picture where maybe actually there's many, many different routes that'd be taking me, all these different places here. So if you could imagine a picture like this, then the answer would be, well, there's, then it's going to be a lot of work. The techniques I'm going to describe in this lecture aren't going to work very well. But if we have something like this, which is exactly what we've described, there's only a few possible ways that we can go. And then we call this low highway dimension. Okay, so that is, in this case, the highway dimension would be 4, which is the number of points at radius r on the way to the points at radius 4r, to optimal paths. So the idea is you can think about what is every single possible place that I could try to reach at radius 4r, and I could say, what is the path I'm going to follow to get there? And where is that going to path? Is that path going to cross some location at radius r? So I'm going to any of these far locations here. In fact, I think about all of them. And I'm going to ask at some lower radius, where do I cross? And if I only cross a small number here, then I have what's called a low highway dimension. Okay. And if I have low highway dimension, then it means that there's going to be efficient ways both to compute and to store the all pair shortest path data. Because if you think intuitively here, if you think about what's happening, is that, well, there may be some local information I need within a city like Denver. So for those of you who don't know, Denver is a city in the middle of Colorado, and there's not a lot of other big cities around it. So, I mean, there are cities in that region, but there's a lot of desert and other empty territory around there. So thinking about this, then, if there's only a very few set of cells right here, then there's going to be some structure that we can exploit when we think about shortest paths, as long as we're going some sufficiently far distance away. So this is a really nice theoretical notion of this idea of highway dimension. It's something we can measure. It's something we can study. And we'll look at some examples in grid maps later in this lecture. So I want to say this is 2010. We're going to see some work that was prior to this, but this is a really good explanation that if you have this sort of structure in your map, then you're going to be able to use that to take advantage of, you'll take advantage of that structure to do computation that is efficient. And so there's quite a number of techniques that have been developed. We'll talk a very brief introduction to contraction hierarchies in a different video. We're going to talk about transit node routing. We'll talk, so we've talked about reach, and there's a number of other things. Even the swamps, why are swamps going to work well, or generally when are they going to be effective? They're going to be effective when we have something like this lower highway dimension. So there were a number of people that were using these properties, and then this is sort of the description of low highway dimension that is going to describe them to us. And I'm going to use this, we'll use this sort of picture here of, thinking about this small and this large radius to consider how we might do this overall. Okay, and so highway dimension was something that was developed for doing, this is by Bast et al. I think the first paper was in 2006. There was another bigger paper, or a journal paper in 2007, if I have all those right. But the idea here is that we're going to do some, and this is looking a little bit like constraints. We're basically going to constrain where our paths can go through, and we're going to do some computation about the constraints of where paths can go through, and we'll use that to be able to reconstruct paths and path distances very, very quickly. And so we can even look, and there's a couple of ways, I'll show some different views of the ways this could be done. And I'm not going to get into like all the gory details you have to do to make this work, but we'll work through a number of them in this lecture. So if we look at this picture over here, I'm going to imagine that I have 2 points that I want to find the path between. And imagine that I have this idea, I have low highway dimension, and so I have a few points around each of these. So I'll make these be colored here. So you can just imagine that maybe I only have a few points here around this state, and I have a few points around this state, and we say, as long as I'm going sufficiently far, then all paths from this state, shortest paths from this state to anywhere else are going to go through one of these 4 points. And similarly for this state here, we might say, imagine as long as I'm going sufficiently far, then all paths will be going to one of 1, 2, 3, 4 states here. Now we think about this. If I've computed, and we'll compute this, think about an exact computation. So if I know exactly this distance, I'll make this a little bit darker. If I know exactly this distance here, this distance here, this distance here, and this distance here, I know what these shortest paths are, then that's going to be a start for what's useful here. But then the second thing that I can do is I can compute the shortest paths between all of these points here. And we're going to call these blue points transit points. So we can imagine here that I've computed for all of these. Maybe I won't draw all of them because it gets a little bit messy, but you can imagine that I've got all of these distances computed. Okay, so what I have is for every point in the map, I know what its transit points are, and I know the distance to those transit points. And then for all transit points, I know the distance between them. I might store the paths as well. We'll talk about some of the differences in an upcoming lecture between storing paths and storing distances, and some interesting trade-offs there. But anyway, you can imagine I have something like this. And so if I want to answer the query, or I want to know basically how far is it from here to here, then all I have to do is for each of these transit points, I can query them relative to each of these other transit points. And I basically say, well, look, in this case, there's 4, and there's 4, there's 4 here, and there's 4 here. And so if I just look at all pairs of those, there's 16 possibilities of ways that I can travel. Let's say from here to here, I could go to here, and then to there, here to here, and then to there, and here to here, and then to there. Okay, so that's 4 possibilities, and there's 4 sort of ways I can do it here. And then for each of those, there's 4 ways here. So in this case, there would be 16 possibilities. Between our 2 cities. And so what I would have to simply do is if I know this distance, and I know this distance, and then I know that distance, then these are going to give me and in fact, if I know that these are shortest paths, I know that these are shortest paths, and I know that all shortest paths go through these 4 points, then by simply comparing these 16 possible routes, from that I'll be able to extract what is the shortest path between these 2 states. Okay, or at least the distance of the shortest path between these 2 states. So this is this is going to work really nicely, and the reason why it's going to work well, or why it might work well, is if I have a very low highway dimension. So over here, if there aren't very many states, in particular these transit routes, transit points or transit nodes, if there aren't many of those, then it won't be very expensive to store the all-pair shortest path between them. And additionally, it won't be very expensive for every state here to actually store the distance to these transit points. Okay, so this is the general idea that we could follow, and this is the idea of transit routing. And so I can take now a really, really, really long path, and normally, you know, the computation of a shortest path for a very long path would be very expensive. But in this case, you can see it doesn't matter how far these states are apart. I'll actually be able to calculate the path length between them in just, well, if the highway dimension is h here, or so the number of transit points for each node is h, then it's sort of h squared time. In this case, I would look up 16 possible routes, and I would immediately after that know what the shortest distance is between the states. If I've stored the paths, then I could extract out the paths as well. Okay, so this is the basic idea, and what we're going to do is we're going to spend some time looking at some variants on the idea and on the consequences of this idea. Okay, so let me just say, let's just start out by writing this down formally. So what are we computing? So the computation is I want the min for some I and j, okay, where I and j are going to be all my transit points. And so I want the min, so this is the transit routing. At least as a high level. As I said, in practice, there's some details about doing local paths and things like that that I'm not going to talk about, but I'm thinking about this as the, so I and j are transit points, so I want the min of the distance from S to the ith transit point of S, okay, plus, so this is the distance to some transit point I, plus the distance to the ith transit point of S to the ith transit point of of T. So this is for thinking about some ST path. So I have a transit point. I want the distance between the ith, and this should be the jth transit point here, and then plus the distance of transit point j of t to state t here. And just to make this clear, what we see here is there's basically three things: the distance to get to my first transit point, the distance between my two transit points, and then the distance to get from my last transit point back to my goal. And by just iterating over these ij, as long as the number of ij here is small, then this will be an inexpensive calculation. Okay, so this works really well in road networks, as I said, and this is really the beginning of a number of techniques that were developed that we're starting to say we should maybe just be doing all pairs shortest paths, or getting something that is much closer to a representation of all pairs shortest paths than to try and do other heuristic approximation methods. And to say we're going to be finishing up one of these, I don't know if I'm going to do a conclusion lecture yet, but we'll be finishing up the introduction of material with a approach, which is an abstraction of refinement approach. And these were the types of approaches that were being used in road networks prior to the development of these techniques that can use all pairs shortest paths efficiently. And these abstraction refinement techniques do still work very well in some domains, and so we will still be covering those. But for things like road networks that are relatively static, that the shortest paths are very valuable to have, then this calculation and starting to think about these calculations became very important, and a lot of work went in there, primarily in the road networks community. Okay, and so what you had happen then is and I want to just, because we've been using a lot of grids as sample domains, we're going to use these as a way of sort of looking and understanding here, is in 2012, then what happened is Ansfeld et al. Were looking at the question of, can we do this in grids? Now, there was a paper, and I don't remember the exact year on this, by Mayer Goldenberg, that was looking at this. Was looking at the same idea. He called this portal heuristics, and he was able to say that this can be done in grids. But this is a paper by Ansfeld et al. 2012. This appeared in the AIDE conference, AIIDE. And they were asking the question of whether we could do this efficiently in grids. And the initial answer they had is no, we can't. And so I want to just explore a little bit of what's going on here. And in order to do that, we're going to look at some grid maps here. And so here's an example grid map. I'm going to have a live demo of this in a minute, but we're going to analyze this map and think about what happens on this map for a little while. And in particular, what they discovered is that if we weren't careful, there are a lot of symmetries in these maps. And so you could end up with basically fairly inefficient approaches. And so we could think here, I'm just going to choose a single state. We're going to do some of this analysis from a single state and ask this question: is if I choose a single state here, and I go ahead and think about what are the transit nodes that I'm going to have, going to sufficiently large distances, we can sort of analyze what might happen. And so, we can imagine, I'll just start with a point right here, sort of in the middle of this map. And this is going to be our start state. And then we're going to think about going to some sufficiently far distance. So I'm going to just do an approximation of that. Okay, let's see if I can draw this a little bit straighter. And we want to think about, if I'm going to go, what are the states at some short distance here, which are needed to reach all the states at the blue farther distance. And what we'll see is there's some areas down here where the states are just in obstacles, so we don't really have to care about those. We don't have to care about these. Maybe we don't care about that. Maybe we don't care about this down here. And so what we do see here, if I'm going to highlight these and just highlight them in gray. So there's some space here that we care about. We care about this. We care about this. And we care about this. And if we're not careful here, basically, we could end up having this entire gray region, or we could end up having the entire red region be part of the regions that we need to do this transit routing. And so we can end up with a much more expensive computation. And basically, we can end up with high highway dimension. Okay. And so if we look here, for instance, so we've been talking about canonical orderings. And if we remember, the canonical ordering in a grid map says that when we follow a path, we should be taking a diagonal move followed by a cardinal move. And so if I just take this map and I write out what my canonical ordering would have me doing in my paths, is it would have me doing paths that looked like this. And I would come out this way. Coming down here, I would get paths that went out this way. And if I continued out this way, you would also see that the paths would look like this. Okay, and we would come up here, and then we would continue out in this direction. Okay, and sorry, and there's another think piece here that would have us continue in this direction and out here. And the observation that was made actually by this aid paper was that in grids, and they weren't aware of canonical orderings at the time, they were not something that had been well described in the literature. But if you look at something like this, what we can see here is from the start state, we would actually, if we think about all the paths to reach, like what is the path that reaches here? It's this path. What is the path that reaches here? It's this path. And so if we go back to this red line here of states that are near to the start state, getting to states that are far away, we would actually see in our canonical ordering that our canonical ordering would take us through, when we find the shortest paths here, it would actually take us through every single one of these states along here. It would take it through all of these states. These states don't go anywhere, so we wouldn't hit them. But we would hit all of these states as here as well as we were coming down through here. And then there's nothing around here, so we wouldn't need any of these states here. But you can see that there's quite a large proportion here of states, which I'll do it on, which would be needed to be able to, as part of our highway dimension. So a naive looking at this in a naive way, for this state, we would see that it doesn't have a highway dimension, which is maybe a constant, which is what we'd prefer, but as a highway dimension, which is actually, relative to, sort of relative to the number of states on this border here. We haven't gotten a large reduction. And so this is the problem with trying to do this in a grid map. See, in road networks, we tend to have roads, we build very small roads that lead us, and then we take these roads over long distances. But in open maps like this, where we don't have the structure of a road, then we really can go in quite a few different directions here. And this essentially eliminates the low highway dimension that we would see in a road network. But that actually doesn't mean that all is lost. And so what Ansfield came up with here was that this idea that what we're going to do is we're going to randomize the weights by very, very small amounts. So we're essentially going to create a canonical ordering, but we're not going to create this one because this one works really bad. And the hope is by creating a separate canonical ordering, maybe we can get a lower highway dimension here. So we're going to talk a little bit basically for the next few minutes is how do we actually get a lower highway dimension here. So I'm going to show one way that we can do this. We're just going to go to another copy of this map, which actually comes from doing a canonical ordering. So if I'm looking here, let's just see where I was. I was approximately right here. And my blue radius was going out. Let's just see if I can get that. So actually what I'm going to do is, well, let's do this. So we hope I get something close enough to what we were doing before. Something about like this. Yeah, maybe this last piece is a little bit lower. So here, 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 and there. And what we could notice here is actually that, there are multiple choices for how we build a canonical ordering. And the typical canonical ordering that we've usually done has been to do diagonal actions first, and then taking a cardinal action. But we could also build a canonical ordering that was saying first take a cardinal action and then take a diagonal action. So we can take a look and see what would happen if we were to do this. So what this ordering would do is it would say, in order to reach a state, I'm first going to go in this direction. And then what I'm going to do is I'm going to take diagonal actions after this. So my cardinal ordering will look like this. So canonical ordering, not cardinal ordering. And then if I think about coming in this direction, there is some diagonal action here. I would still have jump points for getting to other locations here. But I'm going to always be trying to take my cardinal actions and then my diagonal actions. So these are going to come down here. Anyway, and so we can continue here. And what we can see is if we do some sort of reverse canonical ordering here, then we do see for a state that's on the border here, when we think about reaching all the states out here, we're actually going to take a straight path here, and then we're going to take our diagonals out here. And so actually all the states that are outside here can actually be reached by one transit point here. Okay, so unlike this map where we said, we're going to go out and then forward, which gave us many, many transit points along here. In this map, because we're going to go out and then diagonal, now we only have to have one transit point here for all of the locations out here that I can reach. Okay, so so coming up with different types of canonical orderings are going to allow us to avoid some of the symmetries that exist in this space right here, and that are going to allow us then to basically reduce the number of transit points that we have. But there's still cases here where we could get many points. And so there's a number of different ways then you could think about, and especially here, for instance, we might say, well, I don't want to just do this one state at a time. I might actually want to take a whole set of states inside here and think about for all of these states, what states do I need to go to on this border so that all of these states will share one set of transit points in order to reduce, instead of having transit points per state, I do it per set of states right here. And so when I start thinking about this now, as I said, I could use a canonical ordering. I could try to build a secondary canonical ordering. I could do some other things though as well, right? I could just do a Dijkstra search and do a search out from here in concentric circles. And then when I get to these states, I can think about just tracing the paths backwards and see where the paths cross this line. I could also think about doing individual searches from each one of the points inside here out until I reach here and see where those different points cross. And so there's basically a number of different ways that we can do this calculation. And in general, there's not necessarily going to be an efficient way to look at all the different possibilities. But we're going to start here by looking at just what some of the differences are. So I'm going to bring up a demo. And in this demo, the way I'm recording this, you can't see my mouse, but I can click here. This demo runs on my webpage, and so there should be a link in the video below, or in the description below. But basically, I can click, and I can drag the mouse around. And as I drag the mouse around the screen, what it's going to show me is it's showing me out here, the blue states are the states that are a far distance. The red states are the states that are at a close distance. And we're seeing which states are on the canonical ordering. And so if I put my mouse right here, which is approximately where we were doing this in our demos, we see exactly what it's describing, that all of these states above the green node in the middle, they're marked in red. So again, I apologize if you're colorblind, but hopefully you can distinguish this. So between the center state and the line on top of that, we see almost all of those states become these transit points, and so we'd have to store a lot of different transit points. And we can see as we move around the map that sometimes maybe there's relatively few transit points, something like down here. There's not too many ways to get out of this room to the rest of the world. The same sort of thing down here. There's not too many ways to get out of this state to the rest of the world from out here, beyond this blue line. So there are some places where we would still get relatively few transit points, but sometimes we would get a lot. And so we can look here as a different one. Here I'm going to do a different search for, in this case, we only have one state in the center, but I'm going to just do individual searches out to each of these points. And so we see sometimes this works fairly well, but when I come out here into open areas again, then I'm still might see a lot of transit points. A third way that we could do this would be by doing a single Dijkstra search, as I was describing, and trying to do some tie breaking to try to minimize the number of transit points. And we see that actually, at least on this map, this is a fairly effective approach. What we see here now is if I rotate through here, so there's the canonical ordering. This is just trying to use individual searches out to the farthest border, and then doing a single Dijkstra search. Because we're following these paths back, and the way we're doing tie breaking, we're ignoring the heuristic, so we're just following g costs out, but we're actually able to get a fairly small frontier here. And you see there's one node for going straight up and getting on the nodes in the top and on the upper right. There's one node for going up and to the left for getting the nodes in the upper left-hand room. There's one node for going basically to the node straight down, one for diagonally down, and one for going off to the right. And so this just shows that by, even in a grid map, where we don't necessarily have low highway dimension, by being careful about the way that we're actually trying to compute these shortest paths, we can greatly reduce the number of transit points that we have. Okay, so here we see there's a lot here, but if I go to this, again, the single Dijkstra search, I can get to a relatively small number of transit points. Okay, so what we can see here is that if we're a little bit naive in a grid, then we might not do very well, but with some careful search, we're able to greatly reduce the number of transit points that we have. Now, the second point that I want to talk about here is something that I mentioned here, and this is thinking about this piece, thinking about doing a number of states here altogether. And I just want to show something which is a fairly simple derivation here. And we'll just see what happens in general. So if we think, let's think about a map here. And what we want to think about is, imagine that if I'm going to take a map, and I could just be very naive about this. And okay, sorry. So I have a map here. And what I'm going to think about doing is, we could think about just saying, you know, I'm going to take this map, and I'm just going to divide this map up into squares. Okay, so if we think about dividing this up into squares, then what we can think about here is, let's suppose that this is, I didn't of course make it even, but let's just suppose this is an n by n map. And let's suppose for the sake of discussion that we made each of these squares to be the square root of n in size. Okay, and so this is giving me, this is a map, we've divided up these points. And so if we think about each of these inside here, for instance, inside one of these cells here, it's the square root of n in size. So if I think about how many cells there are overall in here, that means there's n cells inside here. And if, for instance, for the states inside here, I wanted to do, let's call this a cell. So if I wanted to do in a cell, just inside a cell, if I wanted to do the all pair shortest path, then there would be approximately n squared states. Sorry, let me go back. So there's n states in the cell, and if I want to store the shortest path between all pairs of the states inside here, then I'm going to need n squared states inside that cell. Because this, yeah, so there's n states inside there. Between each of them, we'll store that. And then, so that's going to give me storage inside a cell, and then we can think about what is the size of these lines that are going here. How many states, basically, how many states are there on these lines, on these borders between our states? Okay. And what we can see here is that if we think about the borders between states, then there's going to be n states on one of these lines, and the number of lines that are going to be here is the square root of n. So on the lines, or the borders, there's going to be n states times the square root of n. And if we think about this, we can think about storing then the all pair shortest path between all of these lines here, basically all of these borders. And so if we do that, then what we see here is that we're going to need, so there's n times the square root of n of those, and that basically is going to tell us that we're going to need n cubed for the all pairs shortest path. And so what we can see is that actually now, if I want to take a map like this, and I want to query this map, then I can take any point and any point. I know all of the borders between here. I know all of the distance between these borders because I've stored that here. There's n of them. So there's the square root of n of them here, and then I need, and each of them has n states. So n times the square root of n. There's actually 2 of those because we have to do those in both the horizontal and the vertical direction. But this is going to get me n cubed states. To be careful, it's in a map with n to the 4th overall, because it's the map has n squared states, but all pair shortest path for the map itself between all states would be n to the 4th. To interrupt my own recording here, I just forgot to write one thing down when I was doing this. So here I said that I have n states in a cell because it's square root of n times square root of n. And so when I do all pair shortest path, it's n squared. But I forgot to write down here is that there are n cells in the entire map. And so when I do this for every single cell, then this is going to be times n cells in the map is going to be n cubed overhead. And so what you see here is if you choose these to be the square root of n, then the overhead of within each cell doing the shortest path, n cubed, and the overhead of doing the all pair shortest path of the borders will be exactly n cubed for each of these on an n by n map. So n cubed here is, if there are m states in the map, then this is m to the 1.5. So it's less than the squared overhead that we would see elsewhere. So sorry to interrupt myself there, but I just wanted to point out because I'd forgotten to write the times n factor here. Okay. So by just breaking up the map here and having a distance to all states on my border, plus a distance between all border states in a grid map, I'm already able to reduce, if I think about the number of states on the border, is going to be n times the square root of n, or n to the 1.5, and squaring that is going to be n cubed states in the all pair shortest path, and that already gives me a savings over all pair shortest paths. So I could sit here in a grid and I could just take this entire set of cells here, and that's if I want the shortest path between here and here. I think about all the states that are on the outside, so there will be a computation at runtime, which will be all the states on the outside of here, all the states on the outside of here. I compare their distances and find the minimum, and then this would, in order to store this, I would already have a reduction from n to the 4th to n cubed for getting the all pair shortest path. And so this is the idea that we'll see when we actually want to do transit routing, is we're going to have this choice of how big of a region do I want to do transit routing for. And so I can think about, I can do an entire region here. But I could, for entire region, I could store actually exactly the border of that region, or I could go out to a larger radius. So I have, some radius of states here. For them, I can say, well, I want the distance here to some distance that's farther away. And what we can see here is if I do this, and this is just to make clear some of the details that have to be done to make this work well, is if I'm going to go out to some distance here and know where I am on states that are going to be at least this far away, then what happens here is if I want to make a query between, let's say, a state in here, make this disappear, a state in here and a state in here, I don't necessarily have that information directly available to me. So these sort of short queries are going to become a little bit expensive. But as long as I'm going, if this is like my far distance here, and these are where I'm storing my transit points, if I'm going sufficiently far between two searches, then at least to this far distance here, then I will be able to have some savings in the number. I may have savings in the number of transit points here. So what we're going to do is we're going to look at a demo, and we can just sort of see what happens as we do this transit calculation in a couple different ways. And this question of, well, of course we want to minimize the number of transit points, but as we make the sort of the near and far distances farther away. So we'll go back to this demo here. And if we look at this demo, we're going to clear what's going on here. And we'll look at a couple of different possibilities here. So what we're looking at here is that this is going to be a group of states. And let me just step this. And we're going to say, imagine this case that I've just drawn, where we're just going to think about these states to their border. And then we're going to just iterate over all borders. So here we're really just calculating the border of these states. And what we see here is that of all the states, 100% of the states on the map, 8% of them are going to be on these borders. And so I'm going to do all pair shortest path between this 8% of states. And that's not too bad. And then I will have to do the all pair shortest path between these within these smaller regions. What we do see though is that if I were to be increasing the size or decreasing the size of these regions, basically, if I make the map bigger, then the size of these regions decrease, then what we'll see here is if we were trying to do this calculation here, thinking about all these borders, then the number of states I need is going to be significantly larger. So here, sorry, I have to finish this. We've gone from 8% of the map to 20% of the map. So it's going to be, would be important that the regions here are going to be large enough. But if I go, and we'll just look at this one again, and now what we're going to do is we're going to use so here we're going to take everything within the yellow region. We're going to let the red region be the border where we calculate the transit points. So that's going to be the border of all these states that are marked by the yellow circles. And then our far distance is going to be out to the blue states. So this isn't very far overall. But what we're going to see here is if we do this calculation, we see the number of transit points is being slightly reduced. So if you remember before, we had 19% of the states on the map were transit points. And when we finish this calculation, we'll see what percentage we actually have. So we went from 19% to 15%, and you can see some places where we were able to eliminate some of the transit points. And in the middle of the map, what we see like there's a break in some of the lines, especially when you're getting into little corners of the map where we basically didn't need to store for shortest path calculation some of these borders if we were going sufficiently far away. But we can alternately look at doing this on a larger chunk of the map out to a farther distance. And what we'll see here, before we were using 8% of the map, and now we iterate over the map here, we actually only need about 4% of the map. And so if you look here, we're thinking about is any of these, so we've sort of got these red circle, the squares that are made out of these red circles are saying if you're inside one of those squares, you only need to go through those red points there would be your potential transit points. And in this case, because we've made the near locations correspond to actually where we're doing this, we're able to, let me just show this calculation one more time. So we're still going out, I want this setting here, sorry. We're still going out to this far distance. So we have to be going at least this blue distance away. And basically the farther we make the blue distance away, the fewer states we're going to need. And given that we're doing a good method of selecting our transit points, the farther the blue radius is, then the fewer points we need. And so I just showed this with the blue radius being exactly equal to the size of the square versus making it larger here. And you see we reduced it. The larger we make that large radius, the less work we have to do. However, we get into this case, again, let me just go back and show it one more time. So as we make the larger radius be larger, then we get these points in here where I need to pathfind in something that's not in this large radius, and I won't necessarily have pathfinding queries between states that are inside here. So there's trade-offs between basically how much memory you want to have, how fast you want to go, what your short paths are going to look like by simply setting the radius of your search here when you do this transit calculation. And so there's a lot more things that can be done here, and there's details and there's numerous papers that look at it, particularly in the road network community. You can see some of the different hierarchical ideas that were put together. But this gives us a picture of how we can start thinking about doing shortest paths and computing shortest paths, and how we can take advantage of the low highway dimension, so that instead of having to store every point on these borders here, so even storing every point potentially gets us a savings over all pairs shortest path. But if we have low highway dimension, we're actually maybe going to see even more reductions here. And in things like road networks, where we don't have the ability to sort of arbitrarily travel through the map, then we're going to see even greater reductions from the fact that it costs something to build freeways, and so we don't build very many of them in our actual road networks. So that's going to wrap up this. We'll look at some other techniques for doing things, for basically being able to do efficient all pair shortest path queries, or efficient reductions that are going to rely on this fact that we have low highway dimension implicitly to be successful in practice in a few later videos.